computer. Good. I'll start. So sine of 1, nothing nice. Sine of 2, nothing nice. Sine of 3, sine of 30, we get something nice. Cosine of 30 is not something nice. But sine of 30 is something nice. I wonder what tan of 30 will give me nothing nice. All right. Let me try 60 degrees. Nothing nice. Something nice. Nothing nice. Let me try 90 degrees. A nice number. Now, when we say nice, we mean a nice number to read, a whole number. Yeah? A rational number. Cosine of 90. A rational number is 0. All right. So I'm seeing here that for certain values of theta, I am having sine theta, cos theta, and tan theta being this nice answer or this nice value. One of the values you get, sine of 30 is 0.5. 0.5 is a half. So I write another. Sine of 30 is a half. Cosine of 30, I don't know. I remember that cosine of 60 was also a half. Yeah? Cool. Cosine of 60 degrees was also 1/2. And well, I know the nice value for tan 45 is 1. Tan of 45 is 1/1. Yeah? 1/1. Now, I could actually figure out with these 3 sets of values here, well, 0 and 90 degrees is easy ones as well. I could get it from my calculator. Sine of 0 is 0, cosine of 0 is 1, and tan of 0 is 0. All right? I could plug them in my calculator. Sine of 0 is 0, cos of 0 is 1, and tan of 0 is 0. All right? 90 degrees is the next angle. Now, all right, let the people pass. Only in Trinidad, they go get buying scrap iron or battery buying in the morning. Now, if sine of 30 degrees is something nice, I could figure out a way to express cosine of 30 degrees as something nicer than this. This, as it stands, is an irrational number. This is also an irrational number, root 2. Yeah? In decimal form, it is an irrational number. But in surd form, we could think of it as a rational number. Root 2 is root 2. Yeah? But when I express it as a decimal, it is irrational in nature. Right? Root 2 is irrational, but it looks nicer to have root 2 than to have 1.41423562 and how much ever more decimal places we have. I remember once upon a time, sine, cosine, and tan. What do we know about these trigonometric identities?
Well, you have a couple things. Yeah, you have inverted ratios of them.
Nah, the base ratios. What did we learn about these things? What's the first thing that comes to mind when you have trigonometric identities?
SOHCAHTOA usually does this thing.
What else?
The quadrants.
Before that, maths.
A triangle?
Very good. What kind of triangle?
A right angle triangle.
Right angle triangle. So I know that those sine, cosine, and tan, they have a relationship with a right angle triangle. Yeah? So let me draw a right angle triangle here. We have a right angle triangle here, right? Now, sine of 30 degrees, I'll put in this as 30 degrees. What is sine of 30 degrees in general? Or sine of theta?
So opposite over hypotenuse.
Opposite over hypotenuse. Sine of 30 is a half. It falls into the same form as opposite over hypotenuse. Agreed? So the opposite in this case is looking like it's 1, which will be this. And the hypotenuse looking like it's 2, which is this. Yeah?
Yep.
Good. Now, by Pythagoras' theorem, I can work out this adjacent. Yeah?
Yep.
You can plug it in your calculator, and you'll get the adjacent to be root 3 in exact form. All right? So I have all the values of the sides of my triangle. So I can figure out what cosine 30 is and tan 30 is as an exact value. Yeah?
Yep.
Now, if this angle is 30, what's the next angle on top?
120. So what, 60 degrees?
60 degrees. So this angle here is 60 degrees. So using the same triangle, labeling it a bit different, I now have my opposite to be root 3, my adjacent to be 1, and my hypotenuse to be 2. I can figure out cosine, sine, and tan of 30, cosine, sine, and tan of 60 as exact values, which I can see. So here, I have, I'll do it here. We know that our sine, cosine, and tan of theta. I'll move this table down a little bit. We'll work with 30 degrees first. Sine of 30 is a half. Agreed? Cosine of 30 degrees is adjacent over hypotenuse, which is root 3 on 2. Yeah? And tan of 30 degrees is opposite over adjacent, which is 1 on root 3. Yeah? Good. What about 60 degrees? Space here. Cosine of sine of 60 degrees is opposite over hypotenuse, which is root 3 on 2. Yeah?
Sure.
Cosine of 60 degrees is adjacent over hypotenuse, which is a half. And tan of 60 degrees is opposite over adjacent, which is root 3. Yeah?
Sure.
Now we also have another angle that produces this nice rational number, which is 45 degrees. And again, I can perform the same type of calculations or the same method to work out what is sine, cosine, and tan of 45 degrees. Yeah? I know tan of 45 is 1 over 1, which corresponds to opposite over adjacent. My opposite and my adjacent is here. Yeah? Work out Pythagoras' theorem, you get homeboy here to be root 2. This angle will also be 45 degrees because it's an isosceles triangle. Yeah? So we have the 45 degree angle here. Sine of 45 is opposite over adjacent. It doesn't matter which 45 you pick, you'll get the same answer in both cases. 1 over root 2. Cosine of 45 adjacent over hypotenuse. We get 1 over root 2. And tan of 45 is opposite of adjacent, which is 1 over 1, which is 1. So I have 3 nice angles, and I could get nice values for sine, cosine, and tan of these 3 angles. 0 degrees is one of them, and 90 degrees is the other. But we wouldn't construct a triangle with a 0 degree angle, and we're not going to construct a triangle with a 90 degree angle. All right? But these three values could be get on a calculator. Right? Sine 0, cos 0, tan 0, sine 90, cos 90, tan 90. You could get the values on a calculator. Easy. Now, what is the point of all of this? We'll see. Apart from having our identities 1 to 3 and with big identities 4, 5, and 6, we have other identities that we need to deal with. And the other identities are called double angle and compound angle formulas. Now, there's a particular reason why we will have double angle and compound angle. The compound angle formula is primarily used to figure out, well, what is the value of cosine of something where the something is not a nice value. It wouldn't be cosine 30, it wouldn't be sine 30, and it wouldn't be sine or cosine of 45. All right? It'll be something like sine of 15 degrees. And I'll have to try to figure out how am I going to express sine of 15 degrees exactly. Now remember, these three identities for these three angles, very easy to prove. Once you have a calculator, you can check and see which angles give us nice values. Sine of 30 gives us a nice value. I can put this in my triangle triangle, completely triangle. Cosine of 60 gives me a nice angle, and tan of 45 gives me a nice angle, sorry, a nice value. But sine of 15, just keep in mind 15 degrees, right? Doesn't give me a nice value. Cosine of 15 doesn't give me a nice value, and tan of 15 doesn't give me a nice value. All right? So I can't go and create a right angle triangle and get a exact form or a rational, and I put rational in inverted commas. I can't get a rational answer for sine, cosine, or tan of 15 degrees as yet. That is where the compound angle formulas come into play. Now, the compound angle formulas, it takes a particular form, and the best way to see it is to actually do it. So we have three compound angle. We have sine, cosine, tan. In each of the compound angle formulas, we have two variations to it. All right? So my compound angle formula first, I have sine of A plus B. Next, I'll have sine of A minus B, then cos of A plus B, cos of A minus B, and the same thing for tan. All right, I'll just focus on sine and cosine for now, and a little later down the road, we'll introduce tan, okay? Sine of A plus B, where A and B are any angle, can be any size, is sine A cosine B plus cosine A sine B. Next, we have sine of A minus B. This will be sine A cosine B minus cosine A sine B. 3. Cosine of A plus B. This is cosine A cosine B minus sine A sine B. And finally, we have cosine of A minus B. And this is cosine A cosine B plus sine A sine B. I'll introduce tan as well, right? 5 and 6. We have tan of A plus B is tan A plus tan B all over 1 minus tan A, tan B. And number 6, tan of A minus B is tan A minus tan B all over 1 plus tan A, tan B. Now I can generalize these 3 pairs, and I want you to understand how we generalize it, right?
Plus or minus. It's just plus or minus now.
Plus minus. So this one will be sine of A plus or minus B. So for sine of A plus B, I'll use the operation on the top. For sine of A minus B, I'll use the operation on the below. So this is sine A cos B plus or minus cos A sine B. So I now catered for the two of the number 1 and 2 combined into one formula or one identity.
You said approve these?
Not yet. Cosine of A plus or minus B is cosine A, cosine B. The plus corresponds to a minus in my identity, and the minus corresponds to the plus in my identity. Sine A, sine B. And finally, tan of A plus or minus B is tan A plus or minus tan B over 1 minus or plus tan A, tan B. Yeah? All right. Now, remember I talked about this 15 degrees just now. Yeah? I talked about the 15 degrees just now. How will I express, let's say, sine of 15 degrees in an exact form? So one time we're diving into an example here. We'll do 2 examples, right? This is the application of our compound angle formula. Express sine of 15 degrees in exact form. Now, I've seen this happen already, and students will come and they go think, well, that is the exact form of sine 15 degrees. But the calculator can only express 10 digits. There are more digits. So let me see if we calculate on the computer. I think the calculator on the computer gives a lot more decimal places, and we'll compare both of them, right? Good. So we have that calculator and we have this calculator here. Right? It's scientific. So I want to figure out what sine of 15 degrees is. Okay, good. So look at how much decimal places we have here. A lot more than the calculator. Yeah?
Yep.
So the exact form of sine 15 degrees is not 0.2588190045. It's not even 0.2588190045, 1025202623488988376240. It have more decimal places there. But we can express it rationally in terms of surds. And how do we do that rationally in terms of surds? Is we use the compound angle formula. Now my compound angle formula, I have 30 degrees, 60 degrees, and 45 degrees to work with. And the compound angle formula says I can combine angles. I could have sine of A plus B. It could be sine of 20 plus 40. That will give me sine of 60. It could be sine of 100 minus 20. That will give me sine of 80. Yeah? Now, when I plug in A, let me say A is 100 and B is 20. For sine of A plus B, I'll have sine of 100 cos of 20 plus cos of 100 sine of 20. Yeah? You see nothing in mind. But I don't know what sine of 100 is rationally. I don't know what cos of 20 is rationally. Yeah? So I will be forced to use 30, 60, and 45 degrees in my compound angle formulas because I know what sine of 30 degrees is, sine of 60, and sine of 45, cosine 30, 60, 45, tan 60, 30, 45. Yeah?
Okay, so which one is go first? Like let's use the example of 15 degrees, right? Would it go in place of A or B, especially for the subtraction? Technically,
Guys, that is up to you. That is completely up to you.
does it matter?
But it doesn't matter, but you have to be smart about it. I have to figure out how am I going to manipulate 30, 60, and 45 to give me 15 degrees. How am I going to do it? Give me a suggestion. How will I get 15 degrees by using 30, 60, and 45?
60 minus 45.
60 minus 45. Easy. Yeah? So if I want sine of 15 degrees, it's sine of 60 degrees, take away 45 degrees. Yeah? Now, we could have argued a point as well for another angle. Let me think. 90. All right, when I remember it, I know. But there are other cases where we could actually add up two of the angles and 60 plus 45. That'll give us 105. And I think there's another combination of angles to give me 105. When I remember it, I'll go line, right? For now, let's focus on sine of 15 degrees. I know that sine of 15 degrees, as you said earlier, is sine of 60 degrees minus 45 degrees. This takes the form of 2. Yeah? Sine of A minus B is sine A, and A is 60 degrees. Cos B. Now B is not minus 45 degrees. B is 45 degrees. All right? A is A and B is B, and they are separated by a minus.
Okay.
Minus cosine A sine of B. Now, I know what these things are from my little table here. So let me bring the table down, and we're going to use the table in some calculations. Sine of 60, jump across in my table. Sine of 60 is root 3 on 2. All right. Cosine of 45 is 1 on root 2. Now the dot will represent a multiplication process. Cosine of 60 is a half. Okay, no sin. And sine 45 is 1 on root 2. We have two multiplication processes here. This is going to be root 3 over 2 root 2 minus 1 over 2 root 2. The denominators are the same. I can take away the numerators and express it as 1 fraction. And this is in exact form. Now I wonder, is this the same thing as sine of 15 degrees? Let's check and see. Again, sine 15 is that. I'll use the storage function in my calculator and I'll store it in A. Now remember, A will store the whole number to infinity and beyond. Yeah? Root 3 minus 1. Root 3 take away 1 divided by 2 root 2. Start. If I take it away from essentially sine of 15 degrees, if both of these answers or both of these values are the exact same number, I should get 0. I get 0. Which means that root 3 minus 1 over 2 root 2 is indeed sine of 15 degrees. Yeah?
Yep.
All right, let's do another one. Let me do cosine now. Cosine of 105 degrees. How am I going to use 30, 60, and 45 to get 105 degrees?
60 and 45.
60 degrees
Yeah,
plus 45 degrees. I'll jump back up. This will be corresponding to 3.
Mm-hmm. Yep.
All right. So A is 60 and B is 45. No problem. So here I'll have cosine of 60 degrees, cosine of 45 degrees, minus sine of 60 degrees, sine of 45 degrees. Cosine of 60, I jump in my table, is a half. Cosine of 45 is 1/√2. Sine of 60 is √3/2. Sine 45 is 1/√2. Yeah?
Yep.
Looking a little similar to the one above. And you'll find that happening in most of them. They will look similar in terms of their calculations or the method for their calculations. Minus √3 over 2 √2. And this one becomes 1 minus √3 over 2 √2. Obviously, in exact form. Yeah? And there are a number of angles we can use, right? A number of different angles we can get, right? Remember, 0 degrees is included in this list for the angles, and 90 degrees is also included in the list for the angles. So let's say 90 minus 45 is 45 degrees, right? Let me go with 60 minus 45. We do this one as 15. Or the next one is 30 minus 45, yes. So, 45 minus 30. This could have been another one of the pairing of angles to get sine of 15 degrees, 45 minus 30. Right, instead of using 60 minus 45. Right, because both will yield a 15-degree angle when I minus them. All right. And again, these things are very useful, especially when you have to express a sine of an angle in exact form, and you'll have to do it a lot in advance. Yeah.